Hello students, this video lecture will cover section 12.1, tangent lines. Our learning goal for this lesson is to be able to use the properties of a tangent line to a circle. As is usually the case, we'll start with some vocabulary. A tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. The point where a circle and a tangent line intersect is called the point of tangency. So here in this picture we see B, which is the point of tangency of line AB to the given circle. In addition to having lines that are tangent, you could also have rays and segments. So in this case we have ray BA, which is tangent to the circle, and segment BA, which is also tangent to the circle. Our first theorem states that if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So here in the center picture you can see that we have line AB, which is tangent to circle O. And the theorem tells us that angle OPA and angle OPB are both right angles. Now it's been a while since we've seen a proof, so I thought we'd take this opportunity to prove this theorem. So here we're given line N, which is tangent to circle O at point P. We want to prove that N is perpendicular to segment OP. I'm actually going to do this as an indirect proof. So if you remember an indirect proof, the first thing I'm going to do is I'm going to assume that N is not perpendicular to segment OP. Well, what happens if N is not perpendicular to OP? Well, if that's the case, then there must be some other line that does meet at a right angle. So then we get point Q here, where this is a right angle. Now, given that's the case, we should be able to find some other point on the other side of Q. We'll call that point R, where P to Q is the same as Q to R. So let's find that point, which will be somewhere in that neighborhood, and let's connect from O to R. Now let's take a look at what we have here. We have P to Q, which is congruent to Q to R. We have OQ, which is in both triangles, and we have the right angle at angle OQP. Well, if we assume that that is true, then triangle OQP is going to be congruent to triangle OQR, and the reason for that is going to be by side angle side. Well, and if this is the case, that these two triangles are congruent, then segment OP would have to be congruent to segment OR, and that's by CPCTC. So we have this segment is congruent to this segment. Well, if we assume that that's the case, then line N would have to meet here at P, and since the radii of the same circle are all the same, point R would have to be located here. In other words, this line would have to curve around the circle like this. It doesn't actually exist over here. It actually touches at both P and R, 2 points on the circle. Now, we know that that can't happen, because the only way that would happen is if line N touched the circle at more than 1 point. In other words, that line would have to be more like this than the way we have it pictured. And since we're given the fact that N is a tangent, we know that that can't happen. Which means that our assumption that N is not perpendicular to OP must be false. And so that proves what we were looking to prove. So here we have two questions. It says that segments ML and MN are tangent to circle P at L and N respectively, and that segment ED is tangent to circle O at D. And we're asked to determine the value of X in each case. The first thing we should do based on the theorem that we just looked at is we should know that since these lines are tangent, we have to meet at right angles. So what we want to do is we want to go ahead and fill in our right angles. Now, based on what we know about both quadrilaterals and triangles, we can figure out this information. We know that the sum of the angles of a quadrilateral has to add up to 360. So we have 117 plus 2 sets of 90 plus x degrees, and this has to equal 360. And so if we simplify this a little bit, we get 297 plus x has to equal 360. And therefore we find that x has to equal 63 degrees. Solving for the second problem over here, we have 90 plus 38 plus x, and since this is a triangle, we know that this has to add up to 180 degrees. So we have 128 plus x equals 180. And solving for x, we find that x has to equal 52 degrees. So let's go ahead and look at a more real-world type problem. Here we have a picture of the CN Tower in Toronto, Canada. It has an observation deck that is 447 meters above ground level. We want to know about how far is it from the observation deck to the horizon, given the fact that Earth's radius is about 6,400 kilometers. So the first thing that we want to do here is draw a picture. Okay, so I know that my picture is not going to be perfect, but I've added the tower to the photo. Now, our diagram is certainly not going to be to scale, but what we want to do is we want to include as much information as possible. So here we have a rough approximation of what we're actually looking at. Now, if we add in the information that we have about 6,400 kilometers. Now, generally speaking, I like to go to the smaller unit, but sometimes that's not actually reasonable. In this case, if we go to the smaller unit, we would have 6,400,000 meters. So it would actually be better to switch this to the larger unit. So let's go ahead and make this 6,400 kilometers. Now this piece is also going to be 6,400 kilometers, and this piece is going to be 0.447. The question asks us about how far it is from the observation deck to the horizon, which is the point where you no longer see the Earth. So we're looking for this right here, x. So let's go ahead and get rid of the photo so that we have a little bit of space to work. And if you remember, based on the previous theorem, we know that this must be a right angle. And so here we're going to use the Pythagorean theorem. We're looking for one side squared plus the other side, or 6,400 squared. And that's going to have to equal the sum of the other two, or 6,400.447 squared. Now, if we actually simplify this, we end up with x squared equals 6,400.447 squared minus 6,400 squared. Now the difference between these two numbers isn't going to be that large. They're actually really close together. In fact, 6,400 squared is going to be 40,960,000. $6,400.447 squared is about 40,965,721. And for good measure, we'll keep the 0.8. So then you can see that x squared is equal to about 5,721.8. And by taking the square root of this, we find that x is right around 76 kilometers. Our second theorem is actually the converse of our first theorem. So here it says if a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. So here we can use this to determine the length of the radius. So here we have a right triangle where one leg is 10, the other leg is x, and the hypotenuse is x plus 6. So we know that 10 squared plus x squared has to equal x plus 6 quantity squared. So 10 squared is 100 plus x squared. And here we're going to have to FOIL this out. So we have x plus 6 times x plus 6. We have first times first, or x squared. Outer times outer, plus 6x. Inner times inner is plus 6x. And last times last is plus 36. Combining like terms, we get x squared plus 12x plus 36. And that still equals 100 plus x squared. Since there's an x squared on both sides, we can cancel those out. Subtracting 36 from both sides, we see that 64 equals 12 times x. And dividing both sides by 12, we find that x is 5.3 repeating, which is the same thing as 5 1/3. Here we're asked to identify if segment ML is tangent to circle N at L. So what we're really asking is this a right angle? So the way we check that is by the Pythagorean theorem. So we check, is 7 squared plus 24 squared equal to 25 squared? 7 squared is 49. 24 squared is 576. And 25 squared is 625. 49 plus 576 is 625. So what we end up finding out is the Pythagorean theorem does hold true. And so the answer is yes, this is a tangent to circle N at L. And the reason for that is because of the Pythagorean theorem. The Pythagorean theorem states that this is in fact a right triangle. So this is no longer a question. That is in fact a right angle. Our third theorem states that if two tangent segments to a circle share a common endpoint, then those two segments are congruent. So here you can see both BA and BC are tangent to circle O. They both meet at B. So we know that BA and BC are congruent. I actually like to call this the gnome theorem, because I think this looks like a little gnome hat, so I call it the gnome theorem. So if you remember back, here we have a circle, and since it fits exactly inside this triangle, the triangle is said to be circumscribed about the circle. So this is an inscribed circle, and the triangle is circumscribed about the circle. Circle O is inscribed in triangle PQR, which has a perimeter of 88 centimeters. We're asked to find the length of segment QY. Now, one of the things that I want you to remember is with gnome theorem, we know that any one of these hats has to be congruent on both sides. So if we think of the circle with this gnome hat, then these two pieces must be the same. If we think of the circle with this gnome hat, then these two pieces must be the same. And if we think of the circle with this gnome hat, then these two pieces must be the same. So given that information, we know that this must be 15 centimeters. This must be 17 centimeters. Now we don't know the length of those two pieces, but we know there's two of them. So what we can say is 15 plus 15, those two pieces, plus 17 plus 17, plus some unknown value has to equal the perimeter of 88. So here we have 2 times 15 plus 2 times 17 plus 2 times x has to equal 88. So we have 30 plus 34 plus 2x has to equal 88. So we get 2x has to equal 24. And if that's the case, then x must equal 12. So each of these segments has a length of 12 centimeters. So now the length of segment QY must be 12 centimeters. So that concludes section 12.1, tangent lines. We've learned two different properties of the tangent to a circle. And one of those has a converse that is also very useful. Hopefully everything was well understood. And if not, I'll see you soon.